Thank you for your interest in this video presentation of our biofeedback system. My name is Haidekker, and I'm part of the LAMP project. And the primary responsibility of our group is chlorophyll imaging and chlorophyll fluorescence measurement, which is also the basis for the biofeedback system. Two students contributed significantly to this project, whom I would like to acknowledge. It's Danielle Awan and Karen Dong. The goal of the biofeedback system is to regulate the actinic light to maintain a certain and pre-selected electron transport rate in the plant. And it does so by creating an estimate of the electron transport rate, which is based on the photosynthetic quantum yield of the plant's photosystem. We can envision the control system from its components by looking at the core, the chlorophyll thermometer, which measures the plant's chlorophyll fluorescence and estimates the electron transport rate. A controller compares the actual electron transport rate to the pre-selected one and upregulates the actinic light to maintain the pre-selected ETR, which is something that I will present in a demonstration. The entire system is autonomous, and we put the prototype into this demonstration box, which allows us to easily transport it and use it for demonstration purposes. Although it can work on its own, we do have a graphical interface that allows us to monitor and log the data and to influence the process, as I'll show. Some of the components easily recognized is the actinic light itself, a platform where we can place the plant, an optical fiber that carries the fluorescent signal to and from the leaf, and the actual computer box that contains the electronics to do the monitoring and control action itself. I'm going to demonstrate some of the basic behavior with an admittedly rather unexciting potos plant, but it allows me to demonstrate a few of the features, among them a leaf clamp, which is something you can find in other commercial fluorimeters, chlorophyll fluorimeters as well. And quite important for the biofeedback system is a monitoring photodiode in the back, which allows us to keep track of the actual photosynthetic active radiation. A quick first look under the hood shows us the most critical components. First and foremost, there is the optical system in which the fluorescent light and the excitation light are directed onto the fiber. There is the computing component, which is a fairly low-end 8-bit microcontroller. There is a actinic light driver and, of course, the power supply. Let's first take a look at the chlorophyll fluorometer component. It follows the pulse amplitude principle, and the reason for that is that the actinic light causes the leaf to emit a certain amount of fluorescence that is undefined. Only by providing a defined amount of excitation light for a brief moment can we determine the amount of fluorescence that is actually quantifiable and related to the chlorophyll fluorescence of the leaf. In other words, we take two measurements in short sequence. We measure the area under the curve to reduce the amount of noise, and we take a measurement right before the laser pulse fires, and we take a measurement during the laser pulse. The difference between the two is the net fluorescence caused by the known excitation level of the excitation laser. That net fluorescence is dependent on the plant's physiology and should increase with the actinic light, something that I would like to briefly demonstrate. We see here the graphical user interface for the device that allows us to monitor different variables inside the system and that acts as a data logger. I have set it to step the lights up and monitor the fluorescence and the background signal. The background signal would slightly increase because that is the fluorescence caused by the actinic light. The reference is not supposed to change, but the fluorescence should, as the actinic light fires up, strongly increase. The measurement is in progress now, and certain time elapses until the LED comes on. With the LED on, we do indeed see the increase in fluorescence and also the increase in leaf background. The reference is for us internal to verify that the sensor works appropriately. And we see also that the plant adapts to the new levels of light and the fluorescence level drops again. After another few seconds, the light is being turned off and we should see a return more or less to the baseline. Once again, the crucial green line that now returns to its original level is the difference between the no excitation fluorescence level from the actinic light and the level that is from the combined excitation laser and actinic, meaning the net fluorescence. There is another component to that measurement, which is the saturation pulse. We need some sort of normalization to obtain information how much fluorescence there is in the leaf. And the saturation pulse is a short but strong pulse in the millimolar range that causes the reaction centers to close and causes the plant to give off its maximum amount of fluorescence. So while there are repeated fluorescent measurement pulses, every few minutes, the laser gets fired at the maximum intensity, illuminates a brief area of the leaf at a very high level and causes the reaction centers to close, after which immediately we'll obtain a measurement of the maximum fluorescence. From then on, it continues with normal fluorescent measurement pulses. The fluorescent quantum yield, the efficiency of the leaf with respect to the incoming photons, is then determined as the maximum minus the fluorescence normalized by the maximum fluorescence. This is again something I'm going to show in a demonstration. I have started another recording in which the actinic light was increased just slightly at this point, and we're recording now background, the fluorescence, and the maximum fluorescence after the saturation pulse. In this fashion, we're keeping track of the photosynthetic quantum yield, which leads us to the next step of the actual control algorithm. The control algorithm is based on the measured photosynthetic quantum yield. But our target, the controlled variable, is the electron transport rate. We're using the empirical formula under which the incoming radiation, the photosynthetic photon flux density, is used by about 84% times the photosynthetic quantum yield. And based on the estimate of ETR, which is easy to compute, easy in even in a $5 microcontroller, the control area becomes the set point difference to the measured ETR, and it leads to a control action in which the actinic light is adjusted proportional to the control error, to a control gain, and proportional to the time interval between two measurements. Meaning, the more time passes between two measurements and corrective actions, the stronger the corrective action has to be. And I'm going to replace the photos by a small rose. And I'm going to run a 2-hour experiment, accelerated time-lapse by a factor of 60, in which I'm going to show how the ETR set point is being tracked and even adjustable variable set points are being followed. We start with a modest ETR of 60 micromoles, and the first roughly 15-20 minutes of the experiment are equilibration time. During this time, we begin with a fairly low initial light level, because starting out too high is one of the possible reasons why the entire biofeedback system may turn unstable. However, we can see that some 10-15 minutes into the experiment, the dark purple line is already beginning to stabilize. The light levels are approaching their equilibrium, and we are around 57, 58 micromoles now. The other traces you can see are Fmax and net fluorescence. The ETR itself is fairly far down on that scale. I don't have 2-axis programming with the GUI. But the small window in the center actually shows some of the key values in real time, including PPFD and ETR. Now that we're close to the equilibrium, I'm actually going to change the ATR set point from 60 to 80. And we're going to see that the light levels are again adjusted by the biofeedback system to maintain the new and elevated ETR. Right now the actinic is about 1/3 of its maximum power. Some 300 micromoles of PPFD. And the quantum yield is around 50%. So 1 hour in real time into the experiment, I'm going to switch to 80 micromoles. Some flickering is visible in the real-time image on the right, which is the adjustment of the camera's auto exposure. The light levels are very hard to determine this way, but the red curve, the background curve, actually tells us some story, and the background intensity in the small window does this as well. So we can already see the light levels have risen. We're very close to the targeted 80. Again, within 15 or so minutes, the gain intentionally kept low, because again, if the gain is too high, if the steps are too large, the system may actually run into unstable behavior, and usually it means very high light levels. And since we're almost done, I'm going to backtrack. I'm going to switch back to a lower ETR, and we should be able to see how the system downregulates the light to follow the new lowered ETR set point. this happened about now. I turned the target ETR down to 60. So now the measured ETR is greater than the target, and the actinic level correction would be negative. So the light will dim, as the purple trace actually shows us. So we can see that we actually have a control tracking of a set point in both directions. Thank you for watching, and you can find more info at portlamp.org.